All right, folks, in previous lectures, talking about population and evolutionary genetics, we've introduced some ideas about how allele frequencies change in populations. And fundamentally, that's what evolution is: change in allele frequencies in populations over time. We've talked about the power of Hardy-Weinberg equilibrium in diagnosing the mechanisms of change. And we've also talked about the processes of mutation, migration, and genetic drift, all of which can change allele frequencies, which is what we're really driving at with molecular evolution. Remember, inbreeding doesn't cause changes in allele frequencies. So inbreeding itself does not necessarily drive evolutionary change, because inbreeding only changes genotype frequencies. If those genotypes in one form or another, like say the recessive homozygotes, have lower fitness, then that can change allele frequencies, and that's evolution. Inbreeding itself doesn't lead to evolution. But now we're going to talk about how natural selection can change allele frequencies. And just a reminder of our assumptions of Hardy-Weinberg. Remember, we said Hardy-Weinberg holds if there's no migration, no random mating, population is infinite in size, and there's no genetic drift. And in general, it holds if there's no natural selection. So what we're going to talk about now is if we violate that last assumption, if we have some alleles under the force of natural selection. So what does it take to get natural selection to change allele frequencies in populations? Well, first of all, a trait must be heritable. And what we mean by that is it must be under genetic control, not just a random trait and not environmentally determined. Then, a trait must have variation in the population. If a trait does not vary, then natural selection has nothing that it can do to select one trait or another. Maybe this is obvious, but it's something to keep in mind. Traits that don't have any variation cannot be selected. If all individuals have the same phenotype, there's no selection. And then the trait must cause variation in fitness. That is, a phenotype must lead to differential survival or reproduction. And that's really what fitness is. A difference in fitness is a difference in survival or reproduction, which leads to a difference in contribution of that gene or that allele in the next subsequent generation. And so, if a trait is under natural selection and associated with a genotype, allele frequencies can change due to natural selection. Now let's take a moment to dive a little bit deeper into this concept of fitness. As I said in the previous slide, fitness is really the average survival and reproduction of a genotype. One of the ways we can measure changes in allele frequencies by natural selection is by measuring that fitness. Evolutionary fitness is different than individual fitness, a term we use in common parlance to mean things like strength or speed or something like that. Evolutionary fitness is this measure of contributions of genotypes to the next generation. Let's use head color in these Gouldian finches. That's the name of these finches. And we know that there are three different head colors: yellow, red, and black. And we also know that these head colors are under genetic control. And lastly, we know that these head colors lead to different mate preference choices, so that some head colors tend to produce more offspring in a given environment. Pay attention to that, in a given environment. I'll come back to touch on that in a moment. So there's two different ways we measure fitness. One is absolute fitness and the relative fitness. As you might guess, they're closely related. Absolute fitness is the raw, direct count of offspring an individual produces and contributes to the next generation. So, in this case, I just made up some numbers, but we've got here our three morphs. We've got yellow, red, and black, controlled by genotypes A1A1 for the yellow, A1A2 for the red, and A2A2 for the black. And I just, for the sake of demonstrating this, said, okay, the absolute fitness or the contribution of the yellow head is 2 offspring to the next generation on average. 1.6 offspring for the red-headed ones on average, and 1.2 for the black ones on average. Note that fitness is measured as an average contribution across all individuals who have a particular genotype. Some yellow-headed individuals might contribute six offspring to the next generation, and others might contribute none. But on average, I'm saying that the absolute fitness is 2, 1.6, and 1.2. Pretty straightforward. Well, relative fitness is something we measure relative to the other genotypes. And the way we calculate relative, oftentimes absolute fitness is abbreviated as a capital W. I should have pointed that out in the previous slide. And relative fitness is abbreviated as a small w. Unfortunate that we use W's because lowercase and uppercase matter in this case, but it's the way it's done. Lowercase w is relative fitness, and you calculate the relative fitness of a particular genotype by taking that genotype divided by the absolute fitness of that genotype, we'll just call it A, divided by the absolute fitness of whichever genotype has the max fitness. So, let's take the black morph first. The black morph, genotype A2A2, has an absolute fitness of 1.2, but the max absolute fitness is the yellow-headed morph, which has a max absolute fitness of 2.0. So to calculate the relative fitness of the black phenotype, it is 0.6, 1.2 divided by 2.0. Likewise, for the red phenotype, that genotype has an absolute fitness of 1.6 divided by 2.0, so its relative fitness is 0.8. And the yellow morph, which has the max fitness, 2.0 divided by 2.0, the relative fitness is 1.0. As you might guess, relative fitness is a scale, so it can scale anywhere from 0 to 1.0. So it can vary from 100%, if you want to think of it in percentages, down to 0%. So you might even think of it as, well, the black individuals have a fitness that is about 40% of the max, and the red individuals have a fitness that is 80% of the max. So relative fitness sort of shows competitive advantage. Notice this, absolute fitness measures population growth and contribution to the population growth, while relative fitness predicts evolutionary change. Because the yellow morph in this case is going to have the greatest relative fitness, is going to contribute more over time, and so the population is going to grow more and more yellow. Now I said I'd come back to this, and that's the fact that fitness is something that is always environment specific. We always measure the fitness of a trait in a particular environment. And if the environment changes, it could be from, one lake habitat to a different lake habitat, or if the environment changes over time, it could be from one lake habitat 1,000 years ago to the same lake 1,000 years later. Those environments have changed in both cases, and different genotypes in different environments may have higher or lower fitness. So it's an important caveat. We always are talking about fitness, that is survival reproduction, as only having merit when measured in a particular environment. Type A might do better in one environment, but bad in a different one, and type B might do better in that second environment and worse in the first. We oftentimes think about this as a fitness landscape, where you could think of combinations of genes, or you could think of this as an environment, and the selection will push individuals so that one phenotype in this case is better in this environment, and maybe this phenotype is better in this environment. All right. Next, let's talk about how natural selection can act. There are different ways natural selection can act as a force. Natural selection can act in a directional way. Directional selection is when one genotype has higher fitness than the others. And typically, that genotype is one of the homozygotes. So in this case, on the left here, we see directional selection where the A1 individuals have the highest fitness. The heterozygotes, that's the relative fitness here, have an intermediate fitness, and the homozygotes A2 have the lowest relative fitness. So that A1 allele clearly is more fit, and so the population moves in a direction. No matter where a population first exists, if it's in that environment, even if the frequency of A1 is 0.3, the fitness will only increase for the A1 individuals are going to be contributing more alleles to the next generation, and so the population is going to move up this incline until eventually A1 is fixed. Conversely, directional selection might be acting such that A2 allele is the best allele when you have it in a homozygous condition. So the relative fitness of A2 is equal to 1. The relative fitness of the heterozygote is 0.8. And the relative fitness of the A1 individuals is 0.2. And then, in that case, no matter where a population sits with what frequency of A1, it's always going to be driven to where A1 goes to extinction and A2 is the only allele that is left. So that's directional selection. Another type of selection is called overdominance. Overdominance is where a heterozygote might have a higher fitness than either homozygote. And I'm going to show you a graph with that in a second. And underdominance is when heterozygotes have lower fitness than either homozygote. So let's look at what those fitness landscapes look like if we were to graph those. So overdominance, again, is where we might think of it as heterozygote advantage. The heterozygote does best. Let's look at those relative fitnesses. So here you can see the heterozygote relative fitness is equal to 1. The homozygote A1 is 0.6, and the homozygote A2 is 0.2. So both of the homozygotes have relatively lower fitness compared to the heterozygote. It's heterozygote advantage. If this is the case, heterozygotes are going to do the best. They'll have the highest fitness. What will happen to allele frequencies is if you start out low, at one point, the frequency of A1, heterozygotes are going to drive the population to some intermediate point, an equilibrium point, where you're going to maintain a polymorphism. Because the A2 and the A1 both have lower fitness than the heterozygote, and so this is one of the things that can maintain a stable polymorphism. On the other hand, underdominance is where the heterozygote has a disadvantage compared to either homozygote. Both homozygotes are better. So the fitness here, again, you can see the relative fitness of the heterozygote is 0.4, and the homozygote A2 is 0.8, and the fitness of homozygote A1 is 1. So this is the most fit where individuals are homozygous for A1. But the heterozygote is disadvantaged compared to the other homozygote. Well, if a population starts with, say, the frequency of allele A1 at, say, 0.6, what's going to happen if you could work out your genotype frequencies using a Hardy-Weinberg equilibrium? But if A1 individuals, are doing better, the population is slowly going to be driven up to a point where A1 is fixed. If, on the other hand, you started out with a frequency of the A1 allele, a population did, of 0.1, that population is actually because these homozygotes are have higher relative fitness than the heterozygotes. This is going to slowly be driven up to fixation for A2. There is one point where the frequency of the A1 allele is 0.4, right around 0.4, where there is an unstable equilibrium, where you could maintain a polymorphism, but if there's any stochastic event that drives the population to one side or to the other side of that equilibrium point, the population is going to be driven up to fixation of one allele or the other. Okay, so let's just summarize what leads to divergence in populations due to genetic variation. So, within populations, let's first consider mutation, migration, and some types of natural selection. Mutation will increase genetic divergence. So will migration, because we are increased genetic variation, because we're getting either more alleles through mutation or we're getting more types of alleles coming through migration. And the type of natural selection that can lead to increased genetic variation within populations would be if you have heterozygote advantage, that is, overdominance. Now, between populations, mutation and genetic drift, mutation can also increase genetic variation, but so can genetic drift. Genetic drift, as you'll recall, leads to populations going to fixation for one allele type or another. And if they go to fixation for one allele type or the other allele type, that can lead to increased genetic variation between populations, because one population might get fixed at A1, the other population might get fixed at A2. And some types of natural selection, like either heterozygote advantage, like directional selection, or heterozygote disadvantage or underdominance, can also lead to increased genetic variation between populations. Conversely, genetic drift within populations decreases genetic variation, because genetic drift leads to fixation of one allele or another within a population, so you get lower genetic variation. And the types of types of natural selection that lead to decreases in genetic variation are both directional selection as well as underdominance. On the other hand, between populations, migration decreases genetic variation because migration leads to equilibration between the two populations. So there's less variation between two populations. And the type of natural selection that decreases genetic variation between populations would be if natural selection is driving both populations through directional selection to the same within the same direction. All right, with that, we're going to leave that section of population and evolutionary genetics.